What's up, guys? My name is David. I'm a mechanical engineering student. I'm an undergraduate. I'm around finishing my second year. I'm studying at Gurion University in Israel. So today we'll be doing systems of differential equations, solving them using linear algebra. Alright, so let's go. We have this differential equation. We have three total differential equations. Y prime of t is equal to the matrix times the function y itself. So what do we do from here? We already set that matrix to be A, right? Let's say it's the matrix A. And usually if we want to guarantee one solution to that given matrix, to that given system of equations, what do? We set the determinant minus the unit matrix to be 0. So let's try that out. So to guarantee one solution, we have a minus lambda I. That's some sort of constant, the lambda. So the determinant of that is equal to 0. So what's the determinant of the matrix? We have 3 minus lambda, because the I matrix, if you don't know, is this. This is the I matrix, the unit matrix. So 0, 1. Then we have 2, 1 minus 0, 1, minus 4, oh, minus 1 minus lambda. Okay, so let's determinate it. We'll use the first row since it has a 0 in it. We could also use the last row, but I'll use this. So from here we have 3 minus lambda, and then we have the minor, which is, we take this and this, it's 1 minus lambda times minus 1 minus lambda, minus 1 times 0. So 1 minus lambda times minus 1 minus lambda, and the 0, it's a multiplication of 0, so it's just equal to 0. Then we have minus 0, because we have this coming in now, the 0, plus a 1 over, what's the minor of that? 2 times 0 is 0, minus 4 times 1 minus 1 lambda. So it's 4 over 1 minus lambda, because we have a negative multiplication of a negative. So from here, I don't want to open the brackets, but you can do so. You'll get a polynomial of that matrix, and then you set that equal to 0. We set that equal to 0. Alright, we basically diagonalize the matrix, and we get a lambda 1, 2, and 3, the eigenvalue is set to be 1. Okay, so we have 3 times the same eigenvalue. What do we do from here? So let me delete it. I'll write the matrix for lambda equal to 1. Let's see. So we have a minus lambda for lambda 1 is equal to 3 minus 1 is 2, 0, 1, 2, 0, 1, because it's a 1 minus 1. Then we have minus 4, 0, minus 2. We see that we have the same row twice. What do we do? What do we want to do with them? We subtract one from each other, and then we have, let's say, row 2 minus row 1. 2 is equal to 2, 0, 1. We put the last row up, then we have a line of zeros. Kind of interesting. But we do see that also the second row now, and the third row here, is a multiplication of the first row by negative 2. So we'll do that, and we'll add each other. We'll do row 1 times 2, and then we'll add row 2 and 1, and then we'll get another line of zeros. So from here we get 201 is equal to 0, 0, 0, of course. Here we get 0, 0, 0, 0, 0, 0. What does it mean? We have two free variables. We set that to be equal to the vector x1, y1, and z1, right? So, from the first equation, we get 2x plus 0y plus z is equal to 0. But we also have a y and z which are free because their lines are zeros. So we can choose them to be whatever we want to. So let's say I have these final equations from here. I have 2x is equal to minus z, right? Let's set y to be 0, y1 to be 0, because we can choose whatever we want. But we do not want that vector to be the 0 vector, because it won't give us a general solution for the whole solution, because 0 might be a solution, but, excuse me, we want a more general solution for this equation, for this system of equations. So, let's see, I want a simple vector. So if I choose z to be equal minus 2, we get 2x is equal to minus 2. 2x is equal to 2 divided by 2, and then we get x is equal to 1. So from here, we get that vector 1 is equal to x is 1, 1, y is 0, 0, minus 2, because we set z to be minus 2. We can set a variable to be something only if we have it lines of 0. If we had, let's say, 1 here, y wouldn't be a free variable. Only z would be. Keep it in mind. Keep it in mind. So, this is the first vector. I'll write it here. v1 is equal to 1 minus 2. Let me get another marker. This is the first vector. All right. So how do we get the second vector? As I said, we have two free variables, so we can choose y to be whatever we want. But we still have that one equation, 2x is equal to minus z. This is the equation. So let's see, we want to create a second vector. We want to know what v2 is. So I'll change a marker. V2, how do we get V2? So we can have this equation, right? 2x is equal to minus z. I really hope you can see it. And it doesn't reflect the light. We can set z to be fs. We can set, I'm sorry, my Hebrew spoke out. We can set z to be 0, right? Then we get an x is equal to 0, but we can choose whatever y we want. Right, because it's a free variable, it doesn't influence the first equation. So let's set it to be 1. We set it to be 1. So our second vector now, v2 equal to 0, 1, and 0. Interesting, really interesting. So I'll write it down here. This is the second vector, v2 equal to 0, 1, and 0. Let me just put it here. Let's try and find the third vector. How do we find it? How do we compute it? Where's my eraser? Oh, there it is. So I'll erase this. Alright. And I'll write what we did here. I'll write the elementary Gaussian elimination that we did. So then we said R2 plus 2R1. This is what we did from here to get to this. But how does it help us? Let me get this as well. How does it help us? We know in systems of differential equations that some vector has to be, if we have, let's say, three of the same eigenvalue, which was lambda equal to 1. And we have linear like multiplication of it. We need some sort of linear addition to get to the third vector or second vector. Depends on how much free variables we have. Here we have 2. So we already found 2 linearly independent vectors. So we need to find a third one which is linearly independent to them. But it has to be an addition of these 2 vectors. So let's say we have a vector 3. Let's set it to be w of some sort at first. So w3 has to be equal to some sort of constant alpha times the first vector plus, because it's a linear addition, it can be also a subtraction, but times another constant beta times vector 2. So if we plug that in, we have w3 equal to alpha times 1 o minus 2 plus beta v2 is 0, 1, 0. What do we do from here? Since we set it to be zeros here, but we want to find the vector, this is the solution to the vector. We put the multiplication right around here. Alright, let's try it. So, I'll delete it here, and I'll write the matrix. What do we get? We get 2, 0, 1 is equal to alpha, because here it's alpha times 1 plus beta times 0. Then we have 2, 0, and 1 is equal to alpha times 0 plus beta, it's beta. And we have the minus 4, o minus 2 is equal to minus 2 alpha, negative 2 alpha. And then we close the bracket of the matrix. So what do we do from here? Basically, these operations that we did here, what does it mean? We have 2, 0, 1 is equal to alpha. 0, 0, 0 is equal to beta minus alpha. Minus 4, o minus 2, negative 2 alpha. This is row 2 minus row 1. Then we have row 2, row 3, row 2, we had to put it here. I'll write it row 3, plus 2r1. So we get 2, 0, 1, this alpha stays here, 0, 0, 0, beta minus alpha. We have 0, 0, 0, 0 here as well. Interesting, interesting. But what does it mean here? A set of zeros is equal to something. Let's say that we have beta minus alpha. Let's set it to be equal to 0 as well, because it's a constant that we chose, beta and alpha. Therefore, we can get beta is equal to alpha. And let's set it to be 1 for some odd reason, because it's a very good number 1. I don't know why, but it's a very intuitive number. So from here, we get this matrix, right? 2, 0, 1 equal to 1, 0, 0, 0, 0, 0, 0, a lot of zeros. We got to the first equation again, but it's a little bit different since it's equal to 1. Okay. So I'll delete it here. Sorry guys. It might be a big board, but I don't know. My writing is big, I like to write, So we have a 2x plus 0y again plus z is equal to 1. Whilst x, y, and z are free variables. They are free. Okay. So we can choose. We can set z to be equal to 0, y to be equal to 0 as well. Then we get 2 times x is equal to 1. Then we get x is equal to half. 1 over 2, whatever. It doesn't really matter, it's the same number. So, what did we get? We got that W3, the addition vector of them, is set to be a half, 0, and 0. This is the addition vector. This is really interesting, guys. Really, really, really interesting. Let's delete it, and we'll finally get the solution to the equation. So, we do know that, no, this is all 3, but it's also plus alpha. The first vector, which is 1, 0, and minus 2, and beta 0, 1, 0. We set it to be equal to 1 and 1. What do we get? We get that the third vector is set to be 1/2 plus 1 plus 0. 0, 0 plus 1. Then we have a 0, -2, 0. Then we get 1.5, 1, and a -2. This is the real third vector, which is an addition of all of them. Wait, no, it's my bad. I'm wrong. We also have the function of t, because it's in time value. So we put these two vectors to be times of t to guarantee that it'll be linearly independent. So then what we get is the third vector, not w, not the addition vector, but the third vector is equal to what we found, which is a half 0, 0 plus t times alpha. We set it to be 1 and also beta. So we get a 1, 0 minus 2 plus 0, 1, 0. This is the vector. So we get v3 is equal to, and let's see, it's a half, 0, 0. This is w3, by the way, plus t and minus 2t. Just like that. Okay? So what does it mean? Let's add everything again. So the third vector for final this time is set to be t plus a half, t and -2t. This is the third vector, but we do know that the solution to differential equations, if we have system of 3, is, let's say, the first solution of y1 is equal to e to the lambda t times that vector, vector 1, let's say. And then we use superposition to add everything together. So let's do it. Let's write the third vector here again. I'll use a different color for you guys so you can find it. v3 is set to be t plus half, as we found. T plus half, t and minus negative 2t. Just like that. Boom, boom. Okay. Okay, let's delete. Right. Let's write the final solution. Finally, these types of questions are usually this long, but it is what it is. I don't know. It's a fun question to do in the exam. I like it. So y total, let's say y combined, big Y. Let's write it as big Y. Big Y here is said to be, we have 3 of the same eigenvalue. So we have e to the t times, what's the first vector? 0, 1, and minus 2. Second vector, e to the t, 0, 1, 0. Third vector, ooh, this one's good. T plus a half, t negative 2t. We can't say this is the final question, this is the final answer, but why shouldn't we, make life simpler? So let's say this is y of t, right? So y of t from here is equal to b. Let's just add these 2 vectors because it's e and t. So let's say it's e to the t times 1, 1, negative 2 plus e to the t plus a half, t negative 2t. There you go, guys. This is the final solution. Hope you enjoyed the video and it was informative to you. Please leave a like. If you have some sort of question, write me in the comment section. Stay mathin', boys. See you in the next lesson.